4 times 2750. So the frequency of quarter wave resonance for a propagating velocity of this length equaling to that of light would be 2727 kilocycles, such as before. Our actual frequency measured, of course, was 3400 kilocycles per second. So taking our ratio of frequencies or velocities gives us a velocity of 126% of the velocity of light. Hence, this wave is an accelerated wave. So we've broken the speed limit of the velocity of light. Or you might say we might get a ticket from the relativity police in this case. At any rate, going back to our structure over here, we can see how this occurred. Is we're really not having transverse flow between the turns anymore, but the energy is now spiraling due to the complex quantities of induction along the wires in this direction. So we have a spiraling wave around the coil, and this gives us an effective velocity exceeding that of the velocity of light. And this shows a very fundamental error in many texts which give the method for calculating the resonant frequency of a free oscillating coil or a Tesla coil as being related to the velocity of light. So clearly we have to develop a new system of equations to describe this. Now what we're going to do next is build up a system of analog computers where we can study these waves a little better. With the coaxial cable, obviously we'd have to cut the cable open and stick probes inside to make measurements. In this case, focusing in on the voltmeter, when we use the longitudinal resonance structure, the thing is very sensitive, as you can see on the voltmeter, to any type of changes around it. So if you try to get in there to measure it, you can see by me bringing my hand near the coil that a definite shift out of resonance occurs in the meter. And as an example, I'll keep my hand very close to the coil and find the new resonance peak, and it's gone down about 30 kilocycles just by bringing my hand within 3 inches of the coil. And of course, I bring it away, I have to rehunt for the new resonant frequency. So we'll show you how these waves exist in their analog form, and Tom Brown will give you a brief introduction on the relation between the analog computer and the digital computer, and why we have to use analog computers for the study of these waves. And this will constitute part 2 of this videotape.
We hear the word computer quite often these days, but there's actually 2 types of computers. The computer that most people understand is a digital computer, and it's a very effective machine for certain functions. I use it quite extensively in the management of borderland sciences for database management and word processing. We find it in relationship to the study of transverse and longitudinal waveforms. It has very little use. And we can compare the 2 types of computers here. In digital computer, which of course is silicon chips, we have numerical functioning only. In an analog computer, which is a network built up of coils, capacitors, and various physical things, we have physical functioning as well as numerical. In the digital computer, we have no measurement of function as possible. While in the analog computer, we have direct measurement possible at any point. So you can stick probes in there and find out what's happening at all different sections of the waveforms, where you can't do anything like that on the digital. The mathematical form of the digital computer is dissimilar to that of the wave under study, in fact somewhat inimical to it. And the mathematical form of the analog computer is identical to the wave under study. It's an actual structure in space representing what the wave is. And the digital computer cannot be connected to actual operating electrical system directly, but an elaborate interface must be employed. So you're not really getting a direct relationship between what you're doing. Its interconnection must be used. While analog computer can be directly connected to the electrical system and thereby perform operation upon actual waves. So we find in the analog computer that it's an actual tool for the studying of these waves, and a very promising laboratory tool. And now Eric Dollard will give a practical demonstration of analog computers in the study of transverse and longitudinal waveforms.
In our analog study of electric waves, we'll start with an element of what we've been working with, which should be one pair of wires. And we'll call this the element of transmission, a differential element, as indicated by this symbol here, of an elemental length, which either be 1 centimeter, 1 inch, 1 foot, or 1 light year, depending upon what you want to take as unit length. So this is a little slice of the transmission section. This can be a little cut out of 2 wires of the coil, or it could be the center wire, this being the shield around the coax. The direction of longitudinal flow in this element will be in this direction, and the direction of transverse flow of this element will be in this direction. And we can see these 2 flows occur at right angles to each other. And in the case of the Tesla extra coil, they'll perform a complex addition, and we'll end up with a spiraling wave going up around the coil. Okay, now our analog of the magnetic field of the wires can be a pair of inductance coils, filter chokes or radio frequency chokes or transformer coils or anything that has the ability to store and return magnetic energy. The analog of the dielectric field will be a pair of capacitors. And these can be any form from mica to oil, depending upon exactly what you want to do. Now, when we combine these 2 together, then we have the analog of the complete transmission element. And in either case, the energy can go this way or it can go this way. And we have one element here of our analog transmission. And we have some radio frequency inductance coils of 10 millihenries, and we have some high-Q pulse capacitors of 0.047 microfarads. This constitutes one element of transmission. And of course we can propagate either longitudinally or transversely, and we're going to stack these elements up to symbolize and synthesize these 2 forms of waves, and then we're going to get in there with some rather unique detectors and some conventional detectors, and even use our fingers and determine exactly what's going on with these things and see how this correlates with our previous measurements of actual transmission structures and not their analogs. And then we'll finally conclude with some practical applications for these devices in the transmission of electrical energy and industrial scale, and also the use of producing musical sounds and some other things. So we'll move on to our next part here, combining these elements and performing our measurements. So we'll review our test setup here. What we have, we've taken our element that we've shown and compiled these in series to produce on the workbench effectively 31 miles of transverse electromagnetic transmission line. This might be the power line between the substation and load, or it might be a telephone line connecting 2 towns together. We have our audio oscillator. We have a stereo power amplifier hooked up for mono, and that is our generator. We've left the end of the line open circuited, so we're dealing with a quarter wavelength similar as before. Now we have a probe for detecting magnetism, and we have a probe for detecting dielectricity. Coming to the workbench here, we have our audio oscillator. We have our power amplifier, which basically this constitutes our generator. Okay, our magnetic detector consists of a thermomilliamp meter that has a small filament in it that gets hot when current flows through it, and then the temperature of this is measured with the thermocouple and produces a scale on the meter. These are usually considered true RMS meters, and our actual sensor here will be a little ferrite loop stick from an AM radio, and that'll pick up the magnetism. What will pick up the dielectricity will be a plasma detector, which is just a little neon bulb in this case. When we go to longitudinal waves, of course, many more possibilities will be happening, but with the transverse neon bulb is about what works. So what we're going to do is find our resonant frequency here. So the probe.
Show the whole transmission line that we're going to test.
Oh, right. Also, we want to see our transmission line here. We can get that on the video. There we go.
Step behind it. You can lift it up.
Hold it up. So this is our analog of transverse electromagnetic propagation. You can see the capacitors are in shunt and the coils are in series as shown on the board. And it produces a definite geometric pattern. And of course we've got points where we can make measurement here. Now what we're going to do is determine the resonance, again by measuring the dielectric potential at the amp. This time we're going to use the neon bulb rather than the voltmeter. Turn up our power here. And you may be able to hear the thing coming to life. Right about there is our resonance point. Harmonics from the amplifier are interfering with the results a little bit. We also can measure resonance by measuring the amount of magnetism at this end. This actually proves to be a little more sensitive resonance detector. Okay, now with findings we can actually study this wave now and its character. We can probe down the line and see the very characteristic magnetic distribution. So on our first stage here, we have a very measurable quantity of magnetism. Next stage is dropping off. Next stage is dropping down further until finally we get to the end. There's no more magnetism left. Now with the dielectricity we can start from the end, bring the bulb off of overload a little bit, and we can probe down to the next stage. It's a little weaker, and here it's not even measurable anymore. So the dielectricity has dropped off going this way and the magnetism has gone this way. So we can see our classical distribution of magnetism and dielectricity on a TEM line, where the magnetism rises towards the low impedance source and the dielectricity rises towards the open circuit or high impedance load end of the line. Of course, no load being hooked up at this point. And we also can use our fingers too, which serve as very good measuring devices. The voltages are low enough and the frequencies are high enough. Find the coils at the end here getting quite hot, which can be expected. And then they cool right off until the end, no heat is felt. The capacitors down here are cool. And as we get further down the line, we find the capacitors get warmer. So we find that we have a separation of the heating effect, where the dielectric heating effect, understandably, is occurring where the dielectric energy intensity is maximum, and the magnetic heating effect is maximum at the end where the magnetism is most intense. Now what we'll do next is we'll build up this analog computer into a section of longitudinal magnetodielectric transmission, and we'll compare our frequencies. Oh, by the way, the frequency of this is 1520 kilocycles per second. And we'll compare this with the frequency of our next unit, which will be in our next part here. Okay, our test setup again. We've taken our element and rotated it 90 degrees to give us longitudinal rather than transverse flow. But of course, still using the same components in the element. We have our same amplifier. Oscillator arrangement. The amplifier is producing about the same amount of power as before, but now our distributed line looks like this. And it's a quarter wavelength long, being that we have our low impedance, high impedance. Now the length that this symbolizes is indefinite by conventional terms, because this represents wave propagation in counter space, something that's little understanding of exists. The propagation in counter space would be measured in per mile or per centimeter, so we have to figure our length on that, and so little knowledge exists on that right now that we can't give a definite figure. But we can take precision measurements and determine exactly what's going on here. So right now our oscillator is at 3600 kilocycles. That was our resonance point. I'll show put the neon bulb in the end here. Hold our line up so you can see how it's constructed. Be more careful now, because